Okay, welcome to lesson 3.1. Today we're going to be studying quadratic functions in vertex form, also known as vertex graphing form, because this form makes it incredibly easy for us to graph these functions. So we're going to explore the characteristics. This is the equation of a quadratic formula, or a quadratic function, in vertex graphing form. This is one of two types that we're going to look at. So this one will be y equals a times x minus p all squared plus q. We're going to look at the specific roles of a, p, and q and figure out how they help us in graphing a quadratic function. So if you go into Desmos, you graph y equals x squared, you'll come up with a few key points: 0 and 0, 1 and 1, negative 1 and 1, 2 and 4, negative 2 and 4. You'll start to see that symmetry, 3 and 9, negative 3 and 9, and this is what your graph will look like. Arrows to show that it goes on forever. Now if we graph 2x squared, what we're going to do is every time we come up with an x squared value, we plug in a value for x, we're going to square it, then we're going to double it. So your y values are going to go up a lot more quickly. And if your y values go up more quickly with every x, that's going to make a steeper and more narrow graph. So 0 will yield 0 again, but now instead of 1 and 1, we're going to have the point 1 and 2. And then we'll have the point negative 1 and 2, which it almost looks like my black line is on, but that's just because I'm terrible at drawing lines on my dots. Then we're going to have the point, instead of 2 and 4, we're going to be doubling that y value, so we'll now have 2 and 8. Like that. And we'll have negative 2 and 8. Like that. So your graph is going to be narrower and steeper. Finally, our third one here, 1/2 of x squared. If you did the same thing again, plug in 1 for x, so you get 1 squared is 1, and then you'll divide it by 2. So now we have the point 1 and 1/2, and negative 1 and 1/2. And instead of 2 and 4, which we would normally have, you plug in 2, square it, you get 4. Now we take half of that. We'll be at 2 and 2, and negative 2 and 2. And then instead of 3 and 9, you're going to be at 3 and half of 9, which is 4 and 1/2. So 3 and 4 and 1/2 there, and negative 3 and 4 and 1/2 there. If you wanted to go higher, 4 would normally yield 16 because we'd square it. But now we take half of that, so we're going to get 4 and 8, which is there, and negative 4 and 8, which is there. So you can see that as we half this, so the value we've put out here is the one that's in front of the x, so that's our a value. Here the a value is 1, here the a value is 2, here the a value is 1/2, and you can see how they affect the width of the graph. So the width of the quadratic equation, y equals ax squared, in which a equals 1, just like the top one, this is considered to be the normal width. If the value of a is larger than 1, as with this, the larger a becomes, the narrower the width of the graph is, because it spikes the y value up way faster. If the value of a is between 0 and 1, so a fraction or a decimal, then the smaller a becomes, the wider the graph is. Meaning if we went down to 1/3, 1/4, 1/10, 1/100th, your graph is going to get really wide. Alright, you can try those out on Desmos if you have it handy. So determine the role of A when A is negative. So here A is negative, you can plug it into Desmos. You're going to see right away that instead of opening up like our last ones did, these ones are going to go down. And we'll have 3 and minus 9. So basically if you plug in 1, you get 1 squared, but then you apply the negative to it. So positive 1 yields a negative 1. And every time you plug in a positive number, it's going to yield a negative overall result, which means we have to go below the x-axis. So take a look at the next one, minus 3x squared. So 1 would yield negative 3. Oh, we'd have 0 and 0 still. 1 would yield negative 3, and then symmetry on the other side. 2 would normally yield 4, but we're going to multiply it by negative 3, so that would put us down at negative 12, which isn't on our charts here, but you can see that this thing is going to be opening up a lot steeper. Okay, so the 3, being that its absolute value is greater than 0, so if we ignored the minus sign for a second, the 3 is greater than 0, so it still makes it steeper, or sorry, it's greater than 1, so it still makes it a lot steeper, but then we throw the negative on, which means instead of making it steeper up here, it would just flip it to the bottom, but still make it narrower and steeper. And then 1/3, negative 1/3 x, so normally we would have, okay, we'll have 0 and 0 here. Let's use a different color. Nice yellow, it'll show up on the black. So we still have 0 and 0. Normally we'd have 3 and minus 9, but in this case we'll have multiplied it by a third or divide it by 3, and then symmetry on the other side. So we'll have 3 and minus 3 and negative 3 and minus 3. And you notice that your graph opens up a lot wider. Okay, but still down. So if A is negative 1, the width of the graph is still normal. Okay, still normal width as the red dots here. It's just reflected in the x-axis, so it's flipped from up here down to here as if you held a mirror right here. If A is positive, the graph opens concave up like we saw on the last page. And if A is negative, the graph opens concave down like we saw on this page. Determining the role of Q. So plug these into Desmos. X squared, of course, will yield the same one that we've been looking at in the other ones. Now if we go to x squared plus 4, you'll notice that this thing, this vertex here, no longer at 0 and 0, but it's at 0 and 4, so your graph starts right here. But then it still goes over 1 and up 1, then over 1 and up 3, then over 1 and up 5. So it would be, and we'd have symmetry here, and then you'd have your points here. So basically every single point on this graph, 1, 2, 3, 4, 1, 2, 3, 4, has been shifted up 4. So your next points would be 2 off the charts here at positive 12 or 12. No, I guess they'd be right here at positive 11. No, we're adding 4. So they would be at positive 13. Good math, doll. Okay, head in the game. X squared minus 3, so you plug this one into Desmos. And now you'll notice that we've taken this vertex and we've bumped it down to here instead. Okay, so nothing's moved from left to right. Everything is just moved either up or down. So down, every point is down 1, 2, 3 from the original function here, x squared and this one. So then you'd have your next points there and there. And this one down 1, 2, 3 would be there and there. Oops, there. And you can confirm those just by testing them in the actual function. So for example, we should end up with 3 and 6 here. So if we plug 3 into here, we get 3 squared, which is 9, and then 9 minus 3, which is 6. So we should have the point 3 and 6, which of course we do, and we found that point using our different method just by shifting everything down. So if Q is positive, it causes the graph to shift up by Q units. Q units up. Q units up. So here Q is 4, so that would be 4 units up. If Q is negative, cause the graph to shift Q units down. So here Q was negative 3, so that would be minus 3 down. The role of P. Let's plug these into Desmos. We'll draw our original function here, y equals x squared, and see how the new ones compare here. So here, x minus 2 all squared. If you plug this into Desmos, you'll note that the new vertex is right here, 2 over from where it used to be. And then everything else remains in the same proportions, but shifted to right from wherever a point existed on the original function. Here's our new parabola. X plus 3 all squared. So notice that a negative sign, with our Q value it moved it down, but with our P value it actually moves it to the right. And with a positive sign, if you plug this into Desmos, this, you'll note, is going to shift it 3 to the left, but then otherwise everything else just remains in the same proportions, just shifted 3 left from every other point. So 1, 2, 3. And again, if you wanted to plug some into the actual formula, then you could confirm that we have drawn them in the right places here. Okay. And you could also, just to make sure, make a table of values for each of these. If I'm going too fast for some of you. So if we plugged in 2 for x, this would be 2 minus 2 all squared. 2 minus 2 is 0 all squared, so then we'd have the point 2 and 0 as we saw right here. And you could do that for as many values as you wanted, really, for x and y, just to make sure that you got them all in the right place on your graph. So if the value of P will always be inside the brackets with the x, okay? If there is nothing inside the brackets with the x, then P is 0, as with this one right here. Okay, there's nothing with the x in brackets, so P is 0. If the value of P is positive, it causes the graph to shift P units to the left. If P is negative, it shifts it P units right. That's all. Okay, so this is on your notes on page 144 of your textbook, link the ideas. So you can go through that and fill all these in. Pretty simple. You might be able to get most of them just without going to your textbook, but if you need some help, it's right there on page 144. Example 1, so we're going to sketch a couple quick graphs and determine some characteristics of these graphs, okay? So let's start just with making a simple coordinate axes and figure out some values here. So, vertex, right away, we have these two values. So the x value of the vertex is actually minus 1 because we've shifted it 1 to the left, okay? And the y value of the vertex is minus 3, which means 3 down. So let's draw in some things here. 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5, 1, 2, 3, negative 1, 2, 3. Hopefully yours looks a little better than mine. But if it doesn't, don't beat yourself up. And then you can start plugging some points into here. So our vertex is at negative 1 and negative 3, which is right here. Now, A is positive 2, so this means it's going to open up. Now, normally we'd go over 1 and up 1, but since A is positive 2, we're going to multiply all our y values by 2. So we go over 1 and up 2. And you can confirm that if you plug 0 in here, you will get, if you plug 0 in for x, you'll get minus 1 for y. So let's try it. 0 plus 1 is 1, squared is 1, times 2 is 2, minus 3 is negative 1. Sure enough, we got what we expected. Then there will be symmetry, so that will be your other point. And normally then after going 1 over and 1 up, we'd go 1 over and 3 up, 1, 2, 3, but we're going to multiply that by 2. And it doesn't fit on this graph, but if you've got more room, you can do a few more points. And there's our graph. Okay, the next one, negative 1/4 of x minus 4 all squared plus 1. First of all, our vertex. This means we move 4 to the right, so our x value of our vertex is 4. This means we shift up 1. Y value of the vertex is positive 1. So notice that we always flip on the input value, the x value, but we always remain with the same sign on the output value, or the y value. Okay, so our vertex is at 4 and 1, so 4 and 1 is right here. This one's going to open downward, and normally we'd go 1 over and 1 down, but this time we're going to go 1 over and 1/4 of 1 down. So it's not down very far at all, and this will exhibit symmetry on both sides of the vertex. You can plug in a few more points here. For example, if you want to plug in like x equals 8. 8 minus 4 will give you 4. Squared is 16. Then divide it by negative 4, which will give you negative 4, and add 1 is negative 5. So you'd have the point 8 and negative 5, which would be somewhere over here. And then you'd have symmetry over there. So you notice that this is negative 1/4. So this is a fractional coefficient, which means that this thing is going to open up really wide. Okay, hey, that was pretty good. The vertex of each one of these things. The vertex we determined as part of our graphing of it. Okay, so we've already got that. Domain and range. Now, domain is the values of x that this graph will touch. Now, the thing about each of these is that these graphs will go on infinitely to the left and right. No matter how far you go, this will keep going left and keep rising forever and ever and ever, and it'll keep going right and keep rising forever and ever and ever. And this one will keep going left and falling forever. This one will keep going right and falling forever. There's no value of x that we're not allowed to plug in here, because both of these graphs will touch every single value of x infinitely left and infinitely right. Therefore, our domain for both of these functions is x is an element of the real numbers, and that's it. Okay, x can be absolutely any real number that you can throw at it, even root 2 or pi. The range for both of these are going to be different, because the range are all the y values that the graphs will touch. So notice that our first graph, the vertex started at a y value of -3, and then it went up from there. Okay? That means the graph will never dip below -3. So for the first function, the range is only going to be from 3 and up, but it'll go up infinitely. So y will always be greater than or equal to -3. Sorry, I should have been saying -3 all along. So it starts at -3 and goes infinitely up, so it will never be less than -3. So it will be every possible value greater than -3 or equal to -3. But otherwise, within those specifications, y can be any real number as long as we've noted that it's always above or equal to -3. Similarly, for the second function, we take a look at the y value of our vertex. It's 1, so it starts at 1 here and goes down infinitely. It'll never go above 1, so y is always going to be less than or equal to 1. But within that range, y can be any real number, so then we add that y is an element of the reals. Okay. The direction of opening for the first one, pretty tricky. Up for the second one, down. The equation of the axis of symmetry. The axis of symmetry is always going to be the x value of the vertex, because we always have symmetry, left and right of the vertex. So for this second one, the axis of symmetry, okay, you can stop there, that's good. For this second one, the axis of symmetry is going to be x equals 4, the y value or the x value of the vertex. And it will be an equation because it's the equation of a vertical line. X will always be 4 no matter what y is because it's a vertical line. Then for the first one here, again, you just take the x value of the vertex, and in this one's case, the vertex was at -1, so your axis of symmetry is x equals -1. That's it. Then sketch each graph, which we already did. So go ahead and give the OR turns a try here, and if you hit pause, then when you unpause it, I'll put the answers up for you. So hit pause now. So here are the answers for part A. Hit pause if you need to take a second to look at it. Here are the answers for part B. So congratulations on doing them both perfectly, I assume. See you in class.